Hey, what's up, guys? Today we'll be talking about a very important topic in calculus known as integration. So I'm going to try to give you a neat intuition on what integration is actually doing and what the integral actually really means. You'll notice that the study of calculus is typically divided up into two parts: on differential calculus, which you might already know deals with derivatives and rates of change, and then there's integral calculus, which is what we'll be focusing on in this video. Alright, so the word integrate just means combining things together so that they become a whole. Now you might be saying that, well, I already learned how to do this in like kindergarten, you know. And actually you're right to a certain extent, because integrating something in calculus is pretty much just fancy addition. And the reason it's fancier is because in elementary school you learn how to add a finite amount of things. Like, you know, if Sally gives you 6 candies and Susan gives you 10 more, you have 16 candies in total. But integration in calculus deals with a continuous stream of things. So instead of asking you, what if Bob gave you this much candy and John gave you this much later on, and how many are there in all, the question you would be asking in calculus would be something along the lines of, what if Bob gave you a continuous non-stop supply of candy for the next minute? Then how many candies would you have in total? So your natural reaction would be, sweet, that's pretty awesome, but what is the rate that you'll be giving me this candy? If the continuous stream of candy is just going to be, if it's just going to amount to an extra like 3 crumbs of candy per 20 seconds, that's pretty lame. Let's say the answer is that continuous stream of candy flows at a constant rate of 2 candies per second, which is pretty awesome. So now that we know how fast it's coming, the rate, we have something to work with. If we plot the rate at which we're getting candy versus time on a graph, from 0 seconds to 60 seconds, we obviously get a horizontal line, because the rate stays constant at 2 candies per second. At first glance, it might seem kind of weird because we're plotting the rate at which the supply of candy is flowing to you, not the amount of candy. That's why the graph is a horizontal line and it's not increasing, which might seem a bit counterintuitive because the amount of candy is increasing, but you know, the graph is horizontal. But anyway, so the amount is what we want to calculate. Note that this plot is a lot different from a similar plot with only dots at every 1 second interval, because remember that you're getting a continuous stream of candies, not a bulk of candies every so often. This might seem like a pretty it might seem like a pretty stupid distinction right now, because you'd have the same amount in the end. But what if the rate itself was something like this, where the flow of candy speeds up for some time at first, then stays constant, and then slows down? Now it's not so trivial to add up all the candy now. So in the first example, we'd just be like, oh, 2 candies every second times 60 seconds, boom, we get 120 candies. But in the second example, we have to be more creative, because the rate no longer can be just described by a single number, like 2 candies per second, because it changes over time. So what do we do? You know, this whole continuous business is pretty annoying. Life was pretty simple when we just had people giving us set discrete amounts of candy in bunches. Like Sam gave us this much candy and then Sally gave us this much more. But wait, what if there was a way to look at this continuous stream of candy as someone new giving you more candy at every infinitesimal instant in time? So instead of looking at the flow of candies as some continuous non-stop flow from a single person or source, we look at it as many, infinitely many, different people instantaneously giving you particular amounts of candy every infinitely small interval of time. What I mean by infinitely small interval is not that someone new is giving you some candy every minute or second or millisecond or 1/80 billionth of a second, but every infinitesimally small instant of time. Now, given that you're learning integral calculus, it makes sense to assume that you've already dealt with something like this before with derivatives, so you might already be familiar with this concept. So how do we model this? Let's try to figure this out. You know what? Let's say that the plot of the flow of candy is an upside down parabola. Even harder. So now in this case, the flow of candy parabolically gets faster and faster as time goes on. Then after reaching a maximum value, it gets slower and slower. In other words, the little instantaneous people giving you candy start giving you more and more every successive new person you meet as time goes on, then eventually less and less. Okay, well, at a given moment in time, t, what is the amount of candy that particular guy at t is giving us? Well, what is r of t? Just how fast the guy is instantaneously giving us his candy. So if we just multiply it by how long we're assuming that particular guy is giving us his candy, which is an infinitesimally small amount we can call delta t, we get how much he's giving us in total. Well, if we do this and find the amount of candy each little person is giving us at every point in time between the intervals 0 and 60 seconds and add them all up, we'd exactly get the total amount of candies in the period of time. So the delta t is an infinitesimally small chunk of the total 60 seconds, correct? So it should be the same as taking the 60 seconds and dividing it amongst the amount of little guys giving us candy, right? We'll call this amount of little guys n, which we already know is actually infinity, but stay with me. And so the first guy is located at t equals 0, the next guy is located at delta t, the second guy is located at delta t times 2, the third guy is located at delta t times 3, and so on, correct? And some random guy at the ith position is at time I times delta t. So now, instead of saying r of t, we can say r of I times delta t, which is still saying the same thing, but instead of saying that the random guy is at time t, we're saying that the guy has a number I, and once we multiply I by delta t, we get what time he's at. So now, we have this whole new expression r of I times delta t times 60 over n. If we change the limits on the summation to count from I equals 0 to I equals the total amount of people, n, we can get the total amount of candies given to us by all the infinitesimal people. But remember that n, the number of little people, is just infinity, since we broke it up into infinite little chunks of infinitesimally small amounts of time. So finally, we wrap this whole thing with a limit as n approaches infinity. This is what is known as the limit definition of an integral. We broke apart the continuous flow of candies into infinite parts of infinitesimally small size, used the rate function, which described how fast this whole thing was flowing, to find out how fast each little part was giving us candy, multiplied it by the infinitesimal length of time of each little part, delta t, and took a continuous sum of the whole thing. And now we can finally use the properties of the sum, the summation and limit to find the total amount of candies as follows. B-R-I-P-P-I-N-G, I got the V-V-S-I-C-E, flow like a cooler, juice, blame it on my jeweler. This is our final golden answer. Of course, writing down this whole sum and limit the entire time you wanted to define a continuous sum would be very annoying. So instead, we just use this elongated S-shaped symbol known as the integral. The numbers at the top and bottom denote the start and end of whatever controls the rate function. In this case, it is the starting and ending times. And you'll notice that the delta t turned into dt because delta usually denotes a finite interval of something, whereas the d in this case denotes that the interval is infinitesimally small. There are many easier tricks and techniques used to solving integrals instead of always having to rely on the properties of the sum and limit like we did in this video, but you can find some great worked out examples online, or you'll definitely learn some of the techniques in your calculus course. But yeah, that was a pretty awesome process. So we started off with a simple first grade addition homework problem where we had discrete amounts of things to add and extended that logic to the case where there's a continuous stream of things flowing at a rate. In solving this problem, believe it or not, we actually computed the area underneath the rate function. Now, so many people, when they first talk about integration, associate it with calculating the area underneath something. And although this might seem like really cool geometrically, this is just not the correct intuition. And this is also why so many students get stumped when they first see different types of integration in the future, or when they try to think about why the hell the area underneath the velocity curve might have anything to do with how much distance has been traveled this far. But anyways, guys, I hope you really got something out of this video. Thank you for watching, and good luck with the rest of your calculus. So yeah, see you next time.